Hey you guys, this is Mr. Sal. This is just a quick lesson on work and work modeling or modeling work problems, and also rate, time, and distance type problems. So thanks for watching. Don't forget to like, comment, and subscribe. In general, with working with these types of word problems or specific work problems, they're word work problems. We can use any one of these four formulas that we see right here. So we're looking at, for example, maybe two people working together to, usually it's to paint a room or mow a lawn or something like that, right? And then T represents the amount of time it takes them to both do it together. So we can usually figure, or they'll usually tell us how long it takes for one of them to do the job by themselves and then the other person, and then we figure out how long it takes them to work together to do the job, which is why we're adding these two together, like you can see right there. For the most part, this one right here. So, but again, it wouldn't matter which one you chose to use. If by chance the units aren't the same for the time for A and B to complete the work, you got to put the two times in the same units so that you're not comparing different units there. All right, Hannah can paint a room in 12 hours. Destiny can paint the same room in 20 hours. How long does it take for both Hannah and Destiny to paint the room if they are working together? So, that's it, sorry. Small typo. For this problem, I'm going to look at it differently and then we'll solve it using the equation. We'll do it for all the examples for these. So, first I would think about this. We got Hannah's, and then we're going to add Destiny. And when we add them together, right, then we should get that should equal, I guess I'm looking at it in terms of jobs. Okay. Now, what we know about Hannah is that Hannah can paint a room in 12 hours, whereas Destiny will paint the same room in 20 hours. Okay? Now, I'm looking for jobs here, right? Or rooms. I guess they're kind of work examples, so I'm using jobs on this, okay? All right. But I want to compare them using the same number of hours, okay? So it's kind of like common denominator stuff, which you'll see with the equation, okay? So right here I'm looking at 12 and 20, and I'm thinking 60. Just right off the top of my head, right? So Hannah, if we're looking at 60 hours, then Hannah should be able to do 5 rooms.
How'd you get 60?
Then we got Destiny. Destiny can do, she'll paint the room in 20 hours. So if Destiny had 60 hours to work, we would expect Destiny to complete 3 rooms. Now, here's the thing, is if I add these together, right, because that's what we're doing with these two people, we're adding their times together, then we should be able to get 8 rooms painted in how much time? Well, yeah, 60 hours, right? That should be rooms. But what we want to know is how long it would take him to paint one room, right? So what I can do here is divide both of these by 8, right? Essentially making the 8 a factor of 1. I mean, you could divide it by 8 rooms if you wanted to, but it kind of cancels that out. So that gives us the 1 right there. I get 1 room in 60 hours for 8 rooms. So again, I'm just going to simplify that. It's really just hours here, right? So 68ths, this one could simplify, your calculators would do that for you, right? 34ths or 15 halves. So 15 halves hours or 7.5 hours.
How'd you get 5 rooms and 3 rooms?
So just looking back on that, I mean, that may have made no sense at all, and that's okay, because we have the equation to work with. But we do want to compare the same number of hours when we're looking at this, or, I mean, if it was minutes and minutes, or even seconds. And we can see just individually, right, just for the 60 hours, Hannah can do 5 rooms, or should be able to do 5 rooms, and Destiny can paint 3 rooms. Now, there's no tricky business here. We're not going to be like, oh, well, they got stuck in traffic, okay? So we're not going to do that to you on a test. It's just straight across. This is how much time we would expect them to do it together. So the formula I use, right, 1 over A, that's the first person, how long it takes them to do the room. And then B is the second person, and this would be 1 over the amount of time it takes them to do the job right here, right? In this case, we know A, and we'll just say that that's Hannah's work. Hannah can paint the room in 12 hours. And B, we'll say that's Destiny, can paint the room in 20 hours. So this is our equation, and all we need to do is solve for T, and we would be done, okay? What I'm going to do on this is I'm going to find common denominators, and instead of using 60 this time, I'll use something different. All right. For this, I'm going to make common denominators, which allows me to ignore all denominators for this, right? So, I'm going to use denominator of 240t, right? So in other words, I need to multiply the t by 240. But again, it's a factor of 1, so I got to multiply the numerator also by 240.
And you picked 240 because...
I just did 12 times 20.
Okay.
That's it. Could you find something smaller? Certainly. But, I don't know. That was also slightly convenient. So that's 240 over 240t now. And so the 20, I'm going to multiply that by 12 and t. So the 1, I'm going to multiply by 12 and t as well. So now I got 12t over 120t, 240t, dang. That's equal, by the way. And then the 12, I'll need to multiply that by 20 and t also. So 1 times 20 and t as well. That's addition. So now I have 20t over 240t. And now I have common denominators, which is what we wanted. And now we can ignore all the denominators. So I'll just erase this garbage. And this gives me a new equation right here. Well, new, but also the same. And all I'm doing at this point is combining like terms. 20t's plus 12t's is 32t's. And this equals 240. And so from here, all I would need to do for t, which is what we wanted, is to divide both sides by 32. And that would simplify also to 7.5 hours. Right there. So you get the same answer both ways, which is pretty nice. If Chris does a job in 12 hours with the help of Kelly, they can do it together in 3 hours. How long would it take Kelly to do it alone? So this one is, I mean, it's practically the same problem. We just don't know how long it takes Kelly to do the job alone, which is what we want to know. So, I'm going to look at this in terms of rate, which is essentially going to make the equation anyways, all right? So I'm going to start with Chris. Chris can do one job in 12 hours. Okay, so that's our rate, one job in 12 hours. And if I added that to Kelly's, who can do one job in, well, we don't know how many hours. We'll just put K. We can label it though, K hours. Then this should equal the same job in the 3 hours. So it sets up essentially, well, exactly the same way that the equation would. All right, just to compare this, right, it's really 1 over 12 plus 1 over K. equals 1 over 3. The concept's the same as that last problem we just barely did, where we need common denominators so that you can either add them together or just ignore them altogether. And in this case, I'm going to find common denominators of 12k. All right, so the k, the 12 rather, I'm going to multiply it by k. Well, k over k, like this, right? So now I've got k over 12k. And the k, I'm going to multiply by 12, so 1 by 12 also. So this is added to 12 over 12k. And this equals 3. I need to multiply that by 4, so 1 is 4 by 4 as well, but also the k. So that gives me common denominators of 12k throughout the entire equation for each term. Now that I have common denominators of 12k, I'll just ignore them. And I've got k plus 12 equals 4k's. And solving this, I'm going to start by subtracting k from both sides. And I got 12 equals 3k. Finally, just divide both sides by 3, making that 1k. So Kelly, it would take 4 hours. And we would kind of expect Kelly to be a lot faster than Chris in this case, right? Because 3 hours is pretty fast together, whereas one person is taking 12 hours by themselves.
So when it's over.
One inlet pipe can fill an empty pool in 6 hours, and a drain can empty the pool in 9 hours. How long will it take the pipe to fill the pool if the drain is left open? Not that you would do this, right? But it's interesting anyways, maybe. We look at 6 hours and we see that it's a lower number, and we kind of think that it's moving slower because it's a lesser number. But we're talking about filling the pool, right? So it's actually filling it faster than you're draining it. So like if you see something like this on the exam, don't put it's draining faster than you're putting it in, otherwise it gets 0 points. Okay? Just keep that in mind. All right. In this one, kind of like we did with that first one, we should probably be looking at the same number of hours for this. And I don't know, maybe a picture helps. Maybe it doesn't. Who knows? I hope it helps though. Okay, so this is 2 bathtubs. Is it a bathtub? Oh, it's a pool. Sorry, in years past it was a bathtub. This is a pool, and we're going to fill this pool with water, right? And again, I'm looking for comparing the same number of hours on this thing, particularly for 9 hours. Okay, so just if there were no drain in this thing that's pulling the water out right now, in 9 hours, how much of the pool could I fill up? Well, I know in 6 hours I can fill up 1 full pool, right? So this one's full now. But with the extra 3 hours, that took 6 hours, by the way, right? So that was 6 hours just to fill it. We'll just write that in there. So 6 hours. So we got plus 3 more hours. Well, 3 is half of that 6. So I should be able to fill half of this pool. We'll just write that in. That's half the pool right there, right? Now that was just to fill the pool with that inlet pipe. However, the drain in that same 9 hours should have drained 1 full pool, right? So we're going to go into this and we're going to get rid of 1 full pool. All right, so after 9 hours, how much of the pool do we have filled? Half the pool, right? So if we're filling half a pool every 9 hours, then how long is it going to take to fill the full pool? 18 hours, right? So let's add another 9 hours there. We'll make the water purple this time so we can distinguish between the two. Let's add another 9 hours. Okay, well, I'll fill this pool up right here. But then another half right there, right? Well, in that same second 9 hours, then we should be able to drain this pool right here, right? And what do we got left? Now we got a full pool. All it took was 18 hours. Now there wasn't like a ton of work to show on that. I mean, a lot of explanation on that, but it still works. All right, let's look at this with the equation, because everyone hates my pictures. We've got the inlet, right? And we got the drain. Now, since this is a drain, as it turns out, we're gonna be taking that out, so it's really a subtraction problem, just like the ones before, but instead of addition, it's subtraction. And then this should equal, I guess, in terms of time or pools, however you want to look at it. Okay. So the inlet, it will do one pool in 6 hours, and we're going to subtract from that one pool every 9 hours. I just like the equation or the formula gave us. And that would be one pool in some number of time, some amount of time. All right, well, we do want common denominators.
We do 18.
18 should work great, so I'm going to multiply the 6 by 3 and t, and the 1 also by 3 and t. So that gives me 3t over 18t. Just looking for those common denominators. We'll subtract that because now we're looking at the drain. 9 we'll have to multiply by 2, but also t. So that's 2t over 18t. And the t, we just need to multiply by 18. That's pretty nice. So this will equal 18 over 18t. But once again, now that we have common denominators throughout the whole equation for every term, we just ignore the denominators, which gives us 3t minus 2t equals 18. No, just 18. No t with the 18, right? And combining like terms, 3t minus 2t is 1t equals the 18. And we don't even need that 1 there. We'll make it a phantom 1 and be done. T equals 18 hours. All right, distance, rate, time. Yeah. I guess that's what they meant by motion right here. So rate, again, we look at rate in terms of usually miles per hour or dollars per hour because, you know, we like to get paid and we like to travel fast. But we can manipulate that formula, which is kind of a 5.8 thing, which we'll get to. Notice in the second one, we just replaced time and rate. That's because if you multiply both sides by time and divide both sides by the rate, then it switches the time and rate around. Didn't do anything to the distance, right? If you want to look at it that way anyways. And then if we wanted to manipulate that even further, just don't divide both sides by the rate. See, because if we look at it like this, then the times cancel out, and then you got distance equals rate times time. So we expect you guys to be able to at least manipulate these just this much at least. But if you can memorize one of them and then manipulate, you've only got to memorize one of them. And again, usually rate equals distance divided by time is the first one we remember. All right, on the homework, there was no video for this one, which is what I understand. This is the one most people hated.
Yeah.
I hated most of them.
Well,
I
yeah.
figured it out, but I had to like find different YouTube videos.
Fair enough.
Figure it out, that kind of stuff, but whatever.
Okay, let's rate it first. A boat which moves at 25 miles per hour in water without a current. I know this is not a science thing where we're looking at like friction and, I don't know, water resistance, whatever. Just basic boat in the water without a current, and then we have the current with it, right? So it goes 60 miles upstream and then 60 miles back again in 5 hours. Find the speed of the current to the nearest tenth, if it's necessary, okay? So what we know is that they told us how long it's going to take. So that's a time problem right there, okay? And if we look back, right, time, so time is distance divided by the rate on this. But we kind of have two rates, right? The time is going to be the upstream time. Oh, that's upstream. And then it was added, the time was found by taking the upstream and the downstream time. So we're adding those two together. So the upstream time, that's against the current. The upstream, the distance was 60 miles. And the rate would be the rate of the boat at 25. But because it's against the stream, then we're going to take away the current stream. So C is the speed of the current. All right, and we're adding this to the downstream. Downstream, it was also 60 miles. And the speed of the boat, 25 miles per hour, but this time we're adding the current speed because they're going with the current now. And we also know how much time it took, right? It took 5 hours. Okay, so since it told us kind of like the total there was 5 hours, that's why we're using the time formula for this and not distance or rate. Okay, so we have this set up. Actually, this is how it sets up. So all we're doing now is solving this, I guess we would call it a rational expression or rational equation now. Okay, just like we have, what was it, 5.4, maybe 6, whatever. All right, so what I'm going to want is common denominators from all this. So for example, right here I've got a 25 minus C. And then in this other term, I've got a 25 plus C. The 5 is just 5 over 1, which isn't too bad. But I need 25 minus C and 25 plus C in all the denominators, right? So let's just start with 25 minus C. So I'm going to multiply this one by 25 minus C. Well, I also need to multiply this other term by 25 minus C also. So we're looking at multiplying those as factors of 1, which is good. But I also want each of the terms to have a denominator of 25 plus C. So I need to multiply this term by 25 plus C. 25 plus C in the numerator also. All right, and also the 5 over 1, so 25 plus C. All right, well this is great. Now I've got common denominators throughout, so I get to ignore all of them, right? So I'm gonna rearrange that first one that we got. Instead of it being 25 minus C times 5, I'm going to put the 5 in front. Okay, well, this isn't, still doing pretty good. Let's go and distribute the 60s. So I'll distribute into the green parentheses here. Oh yeah, that's from the other distribution there. Okay. Well, that looks pretty good, and we could simplify that at this point. Right, I can combine my 1500s to get 3000. And then this 60C cancels out with this negative 60C. They just zero out there, okay? Now you may be wondering what happened to our C's. Well, we still have some on the left side that we'll need to take care of. And for this one, well, let's do this a little different, okay? So this equals 3000. Let's get rid of that 5. Be nice to get rid of that 5, right? So let's divide both sides by 5. All right. Now, that's pretty good, but we can make this better, okay? What do you guys notice about that purple and green parentheses there? That's the difference of square stuff, right? So what I can do is take my 25s and square them. Oh, man. And then I would subtract this from C, which is also squared, which equals 600. Right, difference of squares. So that's pretty good. Let's see what 25 squared is. That's 625. And from here, right, just to solve the equation, we'll be subtracting 625 from both sides. And yeah, we could divide both sides by -1 just to get rid of the negatives. So C squared, let's just take this back a little bit. I would square root both of these. So that means that C could be 5, but it could also be -5, all right? Now, since we're talking about speed of a current, that's C, which is what we just solved for, and we loved it. We wouldn't really be talking about speed in terms of negative. I mean, maybe if we're talking about direction, perhaps. But 5 will do for that. So it appears that the speed of the current is 5 miles per hour. Well, you may be wondering if there's a way to check, and there is. You just plug it back into that original red equation that we had created, and it would work, you know, if you did it. Sergio can paddle his kayak 6 miles per hour in still water. It takes him as long to paddle 15 miles upstream as it takes him to travel 21 miles downstream. Determine the speed of the river's current. One thing we need to acknowledge on this is that the time upstream, was this right? Did I read that right? It takes him as long to paddle 15 miles. Yeah, the distances are the same, right? Upstream and downstream. Mm-hmm. So we're really looking at the distance formulas for this. But let's set this up, okay? And the two distances are equal, right? So the distance, let's see, distance is rate is distance divided by time. So distance is rate times time, right? Mm-hmm. All right. So the distance upstream. Let's see. We see the paddles kayak in still water, so that's 6 miles per hour. That's part of the rate. But it takes him as long to paddle 15 miles upstream as it takes him to travel 21 miles downstream. His speed upstream is 6 miles per hour. That would be in still water, but he's going against the current right here. So that's his rate that I just put in there. Well, it's not really the distance, as it turns out, as much as it is the time. Because if we try to set this up with the distance formula like we have it, it's not going to work, right? Because we don't have the time that it took. But we do have how long, how many miles it is, right? So we're going to change the distance to be more of a time factor. Time is the distance divided by the rate. And upstream was 15 miles. And then we'll divide that by his rate, which we already have. And this should be equal to his downstream. Downstream, it was 21 miles. And he can paddle it 6 miles per hour, but now he's adding the current speed to that. So hopefully we see, I mean, I thought it was in terms of distance to start out with, but once we saw that it doesn't work, we need to abandon that and go into something, well, one of the other two formulas, whether it's rate or time. Well, now that we have this set up, actually let me write these closer together. And you could use common denominators. Really, if you just cross multiply this, you'll end up with the same thing anyways. So I'm going to use cross multiplication, 15 times 6 plus c. And this should equal 21 times 6 minus c. And now we're looking to distribute the 15 and 21. Well, we remember back when math problems used to start out with an equation like this. And we hated it back then, but we miss it now. So I'm going to put my c's on the left side by adding 21 to both sides. And so I got to subtract the 90 from both sides also to get the c's by themselves. And now to solve this, I'll just divide both sides by 36. And see, that's the speed of the current is 1. That would be in miles per hour. I don't know. We didn't have to box in the c, I guess. And again, we could check that. We could punch that into both into the c's from where we started and just make sure that it does give us an equal amount of time for these. Gerardo and Jennifer leave from the same restaurant at the that should say at the same time, traveling in opposite directions. If Gerardo travels 5 miles per hour and Jennifer travels 12 miles per hour, how long until they are 85 miles apart? I'm not going to use the equation or the formulas to start this off. All I know is that every 1 hour gives us 17 miles apart. So how many hours until there's 85 miles apart? Well, I'll just do 85 miles divided by 17 miles every hour, and I would get 5. 5 hours. So Gerardo is, yeah, he's doing 5 miles per hour in one direction, while Jennifer's going 12 miles the other direction every hour. So every hour they are 17 miles apart, an additional 17 miles apart. But we should use the formulas too, right? Just so we can see how that sets up. And, right, they gave us a total amount of distance. And distance, rate is distance divided by time. So distance is the rate multiplied by the time. So the distance is going to equal Gerardo, and then we'll add to Gerardo Jennifer's distance. Okay? Well, Gerardo is traveling at, that's his rate, 5 miles per hour. And multiply this by some amount of time, plus Jennifer's rate, which is 12 miles per hour, multiplied by the same amount of time, because it's the same t. And in this case, we do know the distance was 85 miles. So just combining these two like terms, right, and we see that 17 come back, 17 t's equals 85, and then we'll just divide both these by 17. And so the time is still 5 hours. So they change this up a little bit. Alan and Cassandra are traveling towards each other from points that are 122 miles apart. But again, the concept is the same, right? So we're closing in that distance based on their speed. They didn't give us the speeds, though, specifically. If Cassandra is traveling 1 mile per hour faster than, that should say, Alan, and they meet after 2 hours, how fast were they traveling? So they did tell us the total amount of time that it takes. So I'm looking at time, which is the rate divided by the distance. Miles. Wait, let me make. Okay. So the time is distance divided by rate is our time. Well, I guess they did give us the distance on that as well.
They want to know how fast each was traveling.
Yeah.
Would that be rate that we're asking?
Well, they do want the rate, but the rate is going to end up being in the formula anyways. So they did kind of give us two different totals on this. What that means is that instead of time equals distance divided by rate, it's possible we could have distance is rate times time. And we'll find out soon enough, okay? Because right now I'm setting this up in terms of time. So in time, which we know is in hours, we should get Alan's. And we are also adding Cassandra's speeds on this, right? Or I guess you could say times. Because they are getting closer together. But in terms of the speed, which is our rate, what we know is that Alan's is just Alan's, but Cassandra's rate. Cassandra's rate is 1 mile per hour faster than Alan, so we're just going to take Alan and add 1. All right, already I'm thinking this is going to change into a distance problem.
On the homework, that's how it was.
Yeah.
Sorry, I didn't notice this was.
No, that's okay. Again, I thought it was going to be a time one, and that's okay, again, because it doesn't matter, right? As long as we can switch between these, this should end up being a distance one. So Alan's distance, well, Alan's rate is, we're just going to say is A. And the amount of time it takes to reach that distance was 2 hours. And then Cassandra's, we can write in terms of Alan's, right? Her rate is Alan's plus 1, but again, it's being multiplied by 2 hours. Now the distance we already know is 122. So this sets up for us, which we can now solve. Again, if I had tried to write this formula in terms of time, I just wouldn't have been able to. Okay? because we're not given either of their distances. So this ends up being 2a. I can distribute this 2. So that's also 2a plus 2. And now I'll combine my a's. 2a and 2a is 4a. And then I'll subtract 2 from both sides. And I'll divide both sides by 4. And I see a, which is Alan's speed or rate, is 30. And that's what we wanted, how fast they were going. And then finally, we know that Cassandra is traveling at 1 mile per hour faster than Alan. So we'll just add 1 to the 30. All right, there we go. Chase left his house and rode his bike into town at 9 miles per hour. Along the way, he got a flat, so he had to turn around and walk his bike back to his house, traveling 3 miles per hour. If the trip down and back took 24 hours, how far did he get before his tire went flat? Well, here's what we know is that the amount of time it took was 24 hours. So I'm going to make an attempt with the time stuff, right? So my time should be distance divided by the rate. Okay? So the time should be the amount of time it took to go. So the amount of time it took to go into town, well, it would be the distance, which we don't know. Distance into town. Divided by his rate, which was 9 miles per hour. And that time would be added to his time back home, which is the same distance, but at a slower rate there, 3 miles per hour. And yes, we do know how long it took. So instead of time, we're going to... I apologize. So into town, that's how far he got before he got the flat. And then he turns around and starts walking back. So in town, into town, to flat tire. I apologize. We'll clarify.
Well, I read that. That's what it looked like.
And the time it took right there was 24 hours. So put that in. Okay. Well, I'm just going to make common denominators on the right, even though you could do it on the left as well. But I'm going to try to minimize how big that number is. So I'm going to multiply the d thirds by 3 over 3. It's a factor of 1, right? So that gives me 3d over 9. The only reason I'm doing this is so I can simplify this expression. So this equals 24 still. And now if I had 1 d ninths plus 3 d ninths, then I'd have 4 times the distance in ninths equals 24. At this point, I mean, there's several directions we could take this. Fine. I'm gonna multiply by 9 on both sides first. Some of you guys would do this in one step, and that's good. So the 9's cancel out here, so I've got 4d equals 180 to 216. Yeah, now we'll just divide both sides by 4. There we go. And that ends up being 54 distance.
65.
54 miles. That was the distance that Chase rode his bike till he got a flat. And he turned around and walked home. That's a long ways. It's a long ways if you ask me, but that's the answer we got. All right, Darius left the party early, traveling 3 miles per hour. 2 hours later, Nicole decided to head out and catch up with him. She ran 4 miles per hour. That's just 1 mile per hour faster, right? How long would she have to run to catch up with him? So before we use the formula on this one, it's not too bad, right? So we'll say that this rectangle here is the party, right? So after 2 hours, then old Darius would be at, well, going at 3 miles per hour. That would put him 6 miles away from the party. Okay? But now, at this same time, 2 hours later, that's when Nicole decides to leave. I don't know if my diagram's great here, but really all we're really concerned about, not necessarily the 2 hours now, it's just that they're 6 miles apart. Well, Nicole is going at 4 miles per hour, while Darius is going at 3 miles per hour. The difference of these is 1 mile per hour. Well, if they're 6 miles apart, and she's only traveling 1 mile per hour faster, how long will it take her to catch up to Darius? Well, she's got six miles to cover, 1 mile every hour. So, well, we could do 6 divided by 1. 6 miles divided by 1 mile per hour gives us 6 hours. And that kind of makes sense there, hopefully, right? She's got 6 miles to cover, and it will take her 6 hours traveling at that speed. Again, I don't know if we're walking here or riding bikes. Well, just to demonstrate this real quick,
No, he's still going.
is in the next hour, she'll cover 4 miles, while he's going to cover another 3 miles, right? So now he's at 9 miles, while she's at 4 miles, which makes them 5 miles apart. And then if we close in another hour, now they're 4 miles apart, and then another hour, 3 miles apart. All right, so we are looking at distances here. So I'm looking at distance is rate times time. We got the two distances. We got Nicole, and we want to know when her distance is the same as Darius, even though we don't really know when that will be. Nicole, we know her rate is at 4 miles per hour, and we'll multiply that by the amount of time it will take. I guess we don't know how much time it's going to take, right? How long she'll have to travel. And Darius, he is traveling at, right, Darius is traveling at 3 miles per hour. It's going to take him the same time, but he gets a 2-hour head start on that time stuff, okay? So that's why we get a t plus 2 right there. And we'll distribute the 3 to solve this. And if we were to solve this, we'd just subtract 3t from both sides. So the amount of time would be 6 hours. So we got 6 hours both ways. I mean, I don't know. I like to draw pictures. I mean, even though I suck at it, right? But it still works.